And today we're going to try and do some example problems as well, so that you have an idea of what sort of problems you can face in the GRE. So in the last session, what we did was in the week preceding, what we did was we looked at the forms of line. We in the last particular session, we found out how to identify if a point lies on a line, how to identify whether a point intersects, or whether two lines intersect with each other or not. And today we're going to see how to actually use all that information in form of some examples. So we've also seen how to calculate the distance between 2 points using the Pythagoras theorem. So let's make make use of all that information today and solve some of examples. Okay, so let's begin. Let's begin. Okay, so here we go. Okay, so today what we're going to do is we have already covered the fundamentals, and now what is left for us is to understand how we can apply those fundamentals. Okay, so the first we won't allow individuals to record this, but we will be able to provide recordings of this on request. So these sessions, they are being recorded by our side, and if you can request, we should be able to share these with you. Okay, so let me continue. Okay, so the first example. Okay, which of the pairs of points from the given options lies on the line y is equal to 2x minus 3? Okay, so there are two ways to go about this example. Okay, the first thing is, and which is probably the simplest, is to start substituting these points one by one into this line, and then identify whether whether we want to whether the point lies on the line or not. Okay, so yeah, great. If somebody has answered, that's wonderful. Let me just quickly go over the process for our other participants as well. Okay, so we want to look at this line. Okay, so this is our line of interest, y is equal to 2x minus 3. Okay, so here's the thing. In all GRE questions, the first thing that you need to do is to eliminate the wrong options. Okay, why that is important is because instead of going about all of these 8 points one by one, what you can do is understand which options are valid and then focus on those. And so, for example, in this particular case, how do we identify which of these options are valid or invalid? Okay, so first of all, for example, what we can do is we can check the slope, whether the slope. So we understand that the slope of this line is positive 2. Okay, and so we know that the run is always positive. So x2 minus x1 should always be greater than 0. Okay, because for any point, x2 is always going to come in later, x1 is always going to come in earlier. Whether the slope is positive or negative doesn't matter. x2 is always rightward along the x-axis. Okay, so here we can quickly see whether there is any point. And so another thing that that is connected to this is that we have to understand that these points may not necessarily be ordered. So for example, in this particular case, let's consider this is x1 and this is x2. So if this is x2 and this is x1, perfectly valid, because x2 appears after x1. Over here, this is x2, this is x1, valid, because x2 is greater than x1. Over here, x2, x1, yes, x2 is greater than x1. Over here, we see that if we declare this is x2, this is 3, and if we declare this is x1, this is 6. So instead, this should be x1 and this should be x2. Why I'm saying this is because this gives us the order for y2 and y1. And we just need to know whether y2 minus y1 is positive or not. If that is positive, that might present a valid might. The emphasis is on the word might. So that might represent a valid option. Okay, so yes, let's say this is y2 minus y1. So this is y2 minus y1 in this particular case is going to be greater than 0. So that's a valid option. Okay, it's not the right answer, but it's just a valid option for now. For this case, 5 plus 5 minus minus 1, this is also valid. 1 minus 0, this is also valid. And 1 minus 4. So this becomes invalid. Why? Because the slope in this particular case, so this is y2, this is y1. So 1 minus 4 is going to be minus 3. Y2 minus y1 is going to be less than 0. So this is an invalid option. Okay, so we are not going to consider D even. And now what we can do is we can start, with one of these points and start substituting them. Okay, so let's start with option A. So option A is 0 minus 3. Okay, so it's going to be minus 3. So we're going to plug in minus 3 instead of the y and 0 instead of the x. So this is equal to 2 times 0 minus 3. So this is 0. So minus 3 is going to be minus 3. So the first option is valid. Does that mean that the second point is also valid? No, we'll have to confirm. So we do that again. Again, for this particular point, we do 4 is equal to 2 into 1 minus 3. And for this, we get 4 is equal to minus 1. So this second point does not lie on this line. So this option is invalid. Okay, let's do the same for all the other valid options. Okay, so for example, for option B, let's plug in the option B. So first point is minus 1 is equal to 2 times 1 minus 3. Okay, so this is minus 1, 2 minus 3 implies minus 1 is equal to minus 1. So this point lies on the line. Let's do for the other point as well. And so we say 5 is equal to 2 times 4 minus 3. And this implies 5 is equal to 8 minus 3 is again 5. So this point also lies on the line. Because we are asked for only one option, we stop our search over here and we say that our correct option is option B. Okay, all right. There are a couple of other folks also waiting to join. So let me just quickly do a brief recap of this question. Okay, as soon as they join in. Okay, right. Okay, so for the folks who have just joined in right now, what we want to do is the question states that which of these pairs of points, lies on this line. So first of all, what we did was we said we can do something. We can find whether all of these points, perhaps, provide. So for example, for a line passing through this point, must its slope be positive or negative? So we, find out y2 minus y1. An important thing to note over here is that the points may not necessarily be ordered. So for example, in these case, A, B, and C, all these options are ordered. So this point comes first, this point comes in later. But for example, for case of D, we understand that this x coordinate is greater than this coordinate. So this becomes x2 and this becomes your x1. Okay, and so this will be your y2 and this will be your y1. Okay, and if we do y2 minus y1, 1 minus 4, the answer is minus 3. Okay, so this means that for any line passing through these points, should be falling, or its slope should be negative. Whereas this line in question has a positive slope. So this option is invalid outright, and the other three options are valid. And what we started was we first plugged in or substituted these values in, first of all, these coordinates in this line, and then this coordinate in this line. So this point lied on the line, but this did not. So this satisfied the equation, this did not. So this is an invalid option, or this option is not correct. Then we started substituting the coordinates in option B. So this point, and so both of these points lie on the line because they substituting them one by one. First, 1 minus 1 into this equation, we get, minus 1 is equal to minus 1. So this point lied on the line. And then 4 and 5, this is the, procedure we have done over here. So I think this is for minus 1. And this is for example, the other option. So this is for the first coordinate. This is for the second coordinate. And we find out that both of these points lie on the line. So this is your correct option. And because the question asks for only one option, we're going to stop over here. We do not need to check for this. And we're just going to say that, okay, because this is a valid option. And the question asks for only one valid answer. And we're going to stop and we're going to say that our question is, the correct answer is B, okay? Right, so let's proceed. So this is, this is a, graphical representation of where these points lie. And in fact, this point B is, the coordinates for these points. So this is 1 minus 1. So this is 1 and -1, and this is 4 and 5. And we can see that if we, draw this in a computer, simulation or any sort of, graphing software, we'll understand that this is what this particular system of equation provides, and these are the points, that they're lying on the line. So this is kind of like a verification that our answer is indeed correct. Okay, right. Moving on to the next question. Okay, so what we want to do is choose all options that represent the equation of a line that intersects with the given line y is equal to x minus 4. Okay, so we're not interested in anything else. We're just interested in finding out all these options. So this can have potentially more than one correct choices, okay? Because the question says that choose all. Okay, so choose all the options that represent the equations of a line that intersect with y is equal to x minus 4. Okay, so the first thing that we understand is that we don't necessarily need to plot this. Okay, the only thing that we need to understand is that if any line has a slope that is equal to the slope of this line, it is parallel to this. And it is only going to be intersecting with this if both of these lines are collinear. So for example, if this is, for example, y is equal to x minus 4 should look something like, what does y is equal to x minus 4 should look like? It's going to look something like this, because this is minus 4 and this is plus 4. Okay, so this is what the line is going to look like. And so let's take another line, and if that line is exactly collinear with this line, only that line having the same slope, we can say that that might intersect with this. But otherwise, if any other line has the same slope, but it has a different xy coordinates, it's going to be parallel to this line, and it's not going to intersect. So first of all, let's identify those. So for example, we're going to see that this line, y is equal to x minus 8, has the same slope and has a different set of intercepts. So this line is parallel to our given line. Okay, let's call this L1. So this line is parallel to L1. So this is never going to intersect. So this is not the correct option. Okay, over here we see that this is y is equal to minus x. So the slope is -1. So the slope is not the same. So this is correct. This is going to intersect with our line. Okay, over here we have another line, 2x plus 1. This is going to intersect with our line somewhere. Okay, so let's say if we look at this, y is equal to 2x plus 1, it's going to be going somewhere, over here. All right, or maybe something like this has a slope. But if we extend it, back further, it's going to extend with our line somewhere because the slope is different. So this is also a valid option. And let's look at this, line. And this is y is equal to 3x minus 8. So over here as well, this line is also not parallel to our line. Okay, so here the thing is that this line is y is equal to 3x minus 8. So it's going to be looking at something like something like this. Okay, so over here its y-intercept is going to be probably around, it's going to be at -8, and it's going to intersect with our line. Okay, it's going to intersect with our line again. Why? The key giveaway is this slope. Okay, yeah, absolutely. The key giveaway is this slope. If this slope is not the same and the intercepts are also different, okay, so this tells us that these lines will intersect. So B is the only line that was parallel to us, parallel to our line. Okay. Yes, if the slopes are different, that means the lines are parallel. So we understand that if two lines are parallel, they're going to keep on extending both towards the positive and the negative sides towards infinity, but never, because they are parallel, their slopes are the same. They're never going to intersect. So in this particular case, what we are looking for is the options that have different slopes. So we found out that, for example, this line, this line over here, this line B, okay, this line has a slope that is the same as our line. Okay, so this line has a slope that is the same as our line. Okay, for this particular question, yes, if we understand that intersection is dependent upon the slope. But as I said, there is one special case. So for example, if I said that I have another option, y is equal to x minus 4. Now this is the line itself. Let's call this L2. And this line is going to be collinear with our line. So this is going to be intersecting with our line at each and every point. Again, why? Because this is collinear. So this lies exactly on the line itself. So this is, this is a special case that the slope is the same, but this line intersects. Again, why? Because this is collinear with our line. This lies on our line. So this is going to be intersecting with our line at each and every point. Okay. But for any line, any other line which has the same slope but a different set of intercepts, they're not going to intersect with each other because they are parallel. Let me go to the next slide. Okay, so here's the thing. So this is our line. So which one is our line? Can somebody quickly point out? And you can look at this, and this is our line. This is y is equal to x minus 4. What gave this away? This y-intercept, because the y-intercept for this line is if there is another line for y is equal to 2x minus, so here's a question, okay? So if this is 2x minus 8, okay, if this line is going to be, whether this line is going to be collinear, no, unless this is 2y, okay? Because what this tells us, this is 2y is equal to 2 times x minus 4. So, if we cancel this, this just means that this line is actually kind of like a scaled version of our original line. Okay, it's the scaled version of our line. So this doesn't really change. So if we've taken, if we have common factors on both sides, but if the equation was just like 2x minus 8, so that is a different line. Why? Because if we take 2 common, this becomes x minus 4. And then, we divide both sides by 2. So this becomes y over 2 is equal to x minus 4. See the difference? Our original line was y is equal to x minus 4. So this line, 2y is equal to 2x minus 8, is a scaled version of this line. But this line is different, okay? I hope I've been able to answer. Okay, so let's quickly take a look at the pictorial representation. So this is our original line, and we see that y is equal to x minus 8 is a line that runs parallel to it. All other lines, this line. So for example, look at this line, this black line. This line does not intersect as far as the graph that is shown on the screen. But if we extend it, if we extend this line, we can actually see that this line is going to intersect somewhere over here. So over here, we've gone about this question in a roundabout manner. And what is that manner? So we understood that what this question asks is to identify if any line is parallel to it. And that is the only wrong option in this particular question. So over here, y is equal to x minus 8 is the incorrect option. All of these options, other A, C, and D, are correct options. Okay, I hope I've been able to answer and clarify this question. Okay, moving on. Okay, so I have this other question. Next question is, from the given options, choose the line which is perpendicular to the line at y is equal to 2x plus 1 at points 3 and 7. Okay, so what does this tell us? This tells us that we are supposed to identify a line that first is perpendicular to the reference line, y is equal to 2x plus 1. And it is not just any line. It is a line that also is not only perpendicular, but intersects to this line at exactly this point. So let's say y is equal to 2x plus 1. What sort of a line is this going to be? Let us quickly draw this, okay? In fact, because we're solving questions the GRE way, let's, instead of jumping into the math, let's try to solve it the GRE way, okay? Right, exactly. So first of all, we try to identify the invalid options. We find out which options represent incorrect or invalid options. So first of all, we have to see that any line that has to be perpendicular to this should have the slope that is equal to the negative reciprocal of this number over here, or this value over here. So what is the negative reciprocal? So that is minus 1 over 2. So any line that is perpendicular to this line should have a slope y is equal to 1 minus 2. Okay, so with this criteria, or with this criterion, this option is invalid. We don't even need to draw this because the slope is incorrect. Okay, this option is incorrect, again, because this has a slope y is equal to 1 over 2. Now, these are two correct options. or not correct options, valid options. Either of them could be a potential line, and now we have to see. So for example, how, okay, how do we find that out? Okay, just quickly take 5 seconds, maybe 10 seconds, and try to remember, okay, either this line or this line, both of them are perpendicular to this line, okay? But how do we find out that whether this line is perpendicular to our original line at 3 and 7, or this line is perpendicular to 3 and 7? Okay, just take 5 seconds. Try to determine this yourself if there's a way you can do that. Okay, so what we want to do is we understand, yeah, absolutely. What I want is, okay, great. Yes, absolutely. So what we want to find out is whether this point lies on either this line or this line. So simply what we do is we have identified that this is a valid option because the slope is perpendicular. This is also a valid option because the slope is perpendicular. But whether they intersect with this line at this point, that remains to be seen. So how do we do that? We plug in these coordinates in either this or this line. And once we do that, let me quickly do that. Okay, let me do that for Y, for option C first. So 3, 7. So we get 3 is equal to -1 by, sorry, this should be 7. Okay, so 7 is equal to -1 by 2 times 3. Okay, plus 17 by 2. Okay, yeah, absolutely, because this point, and then I'm just going to solve this for simplicity's sake. -3 by 2 plus 17 by 2. Okay, and then if we take the LCM, we don't need to take the LCM because the denominator is the same. So it's simply 2 minus 3 plus, plus 17. So this is 14 over 2. We simplify this, and 7. And so we get 7 is equal to 7. So this point lies on this line. So automatically, this option is correct. And because, again, we were asked for only one option, so we stop over here. We don't need to identify. If, however, the question stated select all options, in that case, we'd have to determine whether D satisfies, or whether this point satisfies this equation as well. But because we were asked for only one option and this option is already correct, so we don't proceed with D, and we say that the option C is correct. Okay, right. So this is what this looks like. So this is your point 37. And for example, so this is your line Y is equal to 2x plus 1, which is the line 2x plus 1. Can somebody quickly determine that? So this orange line is actually Y is equal to 2x plus 1 because it is only this line which has an x-intercept so low along the y-axis. So we know that this is our line Y is equal to 2x plus 1. And we see that this line is also perpendicular to this line, and this line is also perpendicular to this line, but only this line, 3 and 7. Okay, so this line, this black line corresponds to our option C because this is the line that is intersecting with our reference line at coordinates 3 and 7. Okay, so I hope that this has made sense. This is clarified. Okay, moving on to the next example. Okay, right. Okay, so find the equation of a line formed by shifting Y is equal to 3x minus 4 units to the right along the x-axis. Okay, so why I have not probably shown the options over here is because we want to solve this really quickly. And how do we do that? Okay, so instead of drawing this, we get into the solution right away. We don't need to draw this. We just start solving mathematically. So first of all, what we do is, because we're supposed to shift this line 4 units along the x-axis, we find out the x-intercept. Okay, and if we are supposed to find out the x-intercept, what we do is Y is equal to 3x minus 4. We plug in 0 instead of the Y, and we get 3x minus 4. Okay, and then this should be equal to 0, and this implies that 4 is equal to 3x. We're simplifying. We take this to this side, and then we divide both sides by 3. So we get x is equal to 4 by 3. Okay, so this is our x-intercept. Okay, so this is our x-intercept. intercept. And again, now because we are shifting this line, 3x minus 4 is going to look somewhere, something like this. Sorry, shouldn't be, intersecting the origin, should be somewhere over here. This should be minus 4. And this is 4 by 3, okay? And because, if we're going to shift it somewhere over here, so what we are going to do is we're going to take this line and we're going to shift every point on this line to the right by 4 units. So it's going to look something like this, shifted over here. And what is this new x-intercept going to be? So the new x-intercept is going to be, let's call it x new, x-intercept new, is going to be 4 by 3 plus the amount of, or the number of units we're supposed to shift along the x-axis. So this is 4. And if we add them, again, taking the LCM, the least common multiple for this is 3. So we get 4 plus 4 times 3 is 12. So we get 16 by 3, okay? So the new y-intercept, the new x-intercept for the shifted line is going to be 16 by 3. Let me quickly erase this so we have some space for solving this. Okay, so the new x-intercept is 16 by 3, okay? And now, how do we, for example, understand what our new x-intercept is going to be, okay? So that was simple. So this is 3x minus 4. And for this, once we, plugged in 0 over here, we brought in 4 to this side. So we got 4 by 3 as the new x-intercept, okay? So this is the same. This is the same. We see that between the old x-intercept and the new x-intercept, 3 appears in both, okay? In the denominator, 3 appears in both. It's only this value. It's only this value that if this was 16 instead of a 4, we'd get actually 16 by 3, okay? So if I write 3x minus 16, okay, and I plug 0, whether to identify that this indeed is my new x-intercept, I get, bring 16 over here, 16 is equal to 3x, dividing both sides by 3, I get x is equal to 16 by 3, which is my correct x-intercept for the new line. So the new equation for the shifted line is going to be 3x minus 16, okay? I hope that is clear. And we understand from our previous lectures is that, yeah, absolutely correct. We understand from our previous lectures that once, whether we shift, the line along the x-axis or the y-axis, both the intercepts are going to change. And this is what the representation. So this is our original line. So this is 3x minus 4, okay? And this is the shifted line, okay? And as we can see that the x-intercept is shifted over here, but the y-intercept is going to be somewhere down there, okay? It's, if we were able to extend it, the y-intercept is going to be somewhere over there as well. So, the x and the y-intercept both have changed, okay? So this is what our shifted line is going to look like. Okay, I hope this is correct. And then we move forward to our next example. Okay, right. So this example states that find the equation of the line that passes through the point 3, 1 and is perpendicular to the line y is equal to 2x minus 1. Okay, and you're given 4 options. Okay, so we've done something similar in one of the previous examples. The only difference was, for that particular case, what we were given was the point of intersection of the line itself. Okay, so in one of the earlier examples, we were asked to find out the equation of the perpendicular line, which is perpendicular to our reference line at a given point. Over here, that is slightly different. We want to find out a line that, for example, passes through this point, sorry about that, passes through this point as well, and is also perpendicular to the line y is equal to 2x minus 7. So it is not necessarily intersecting with this line as 2x minus 1. It is passing through this point at some stage and is also perpendicular to this line, this reference over here. Okay, so let me just quickly remove these markings so that we have a clear understanding. Okay. All right. Okay. So how do we find that out? So first of all, let's solve this the GRE way once again. we understand that because the slope is m is equal to 2, so the slope for perpendicular line, let's call it m2, okay? So the slope for the perpendicular line is going to be, again, minus 1 by 2, okay? So we find out the options that have a slope of minus 1 by 2. Okay, again, the first two options are incorrect, different slopes. Why? Because this has a slope of 1 by 2. This has a slope of minus 2. So invalid options again. So this option has a slope of minus 1 by 2. And this option also has a slope of minus 1 by 2. Okay, so that is correct. So let's take a look at this line. Okay, so we understand that it has to have this form. All right, and then how do we find out whether this point actually lies on the line? Simplest way, we can, for example, substitute this point in either this equation or this equation, and we can find that out. There's an even simpler way to do that, okay? An even simpler way to do that, in fact, we can identify that as well, okay? But let's do with the substitution, okay? So if we substitute 3 and 1 in this equation, which is y is equal to minus 1 by 2x minus 6. Sorry about that. And we substitute 3 and 1 at the appropriate points. So 1 is equal to minus 1 by 2 times 3 minus 6. So we get minus 3 by 2. This implies that we get minus 1 is equal to minus 3 by 2 minus 6. Okay. And so what does this tell us? This tells us that this is minus 1. This is minus 1 is equal to minus 3 minus 12 over 2. And this is minus 15 by 2. Okay, so this is definitely incorrect. So by the principle of elimination, we've already found out that, we have these options is already incorrect. And once we try to substitute this point in option C, this is also incorrect. So automatically this leaves with only one option, and this should be correct. Okay. In fact, this is a simpler way. The other way is, what we can do to identify, for example, if, we are supposed to find out the equation of a line given we have a slope and a point that it is supposed to satisfy. So over here, because we are given the options, we don't need to get into that, but that point relies on the point slope form. Okay, so if we were, if we were not given these options somehow or the other, and we were supposed to identify, or we were supposed to come up with the equation of a line that is perpendicular to this line and passes through this, what we were supposed to do was we were supposed to, first of all, identify y is equal to 1 by 2x. Okay, and then how do we, identify what is necessarily, how this line necessarily, passes through this line? We use the point slope form, not the slope intercept form, but the point slope form. And what is the point slope form? The point slope form is y minus y1 is equal to m into x minus x1. And what is y1 over here? Y1 is 1. And what is x1 over here? X1 is 3. Okay, let's do that quickly. Y minus 1 is equal to minus 1 by 2 times x minus 3. Okay, so this is y minus 1 is equal to minus 1 by 2x and plus 3 by 2. And so y is equal to minus 1 by 2x plus 3 by 2 plus 1. And if we add 3 by 2 and 1, so we get 3 plus 2 over 2 is 5 by 2. So the x-intercept we get is indeed 5 by 2. So this is one way if you were not given the expressions or you were not given the equations of the line, and you were just supposed to find out, okay, so here's a line, it should be perpendicular to this. So we have known, we have been given the slope. And if we are, given a point, we are supposed to find out the equation of a line without any options being provided. This would have been the way. Okay, thank you. Yeah. Yes, substitution is usually the simplest method, but it is also the most time consuming. Okay, so if you start substituting the point in each and every one of these options, it's going to take time. And as I said, because GRE has different, varieties of questions. So what you need to do is, first of all, use the principles of elimination and identify which options are incorrect so that you don't waste time on them, and simply substitute the answers or substitute the given points to correct that. Okay. Okay. Let me quickly, I then, right? Okay. Let me quickly tell you what I just did. Okay, what I just did was, we've been given the options over here, so this was simpler. Why it was simpler is because we used the principle of elimination. We didn't actually, substitute the coordinates of the point in option D. We just identified that options A and B definitely are incorrect. And then option C is also incorrect, because, points 3 and 1 do not lie on this line. And then we identified that this is indeed the correct option. But what if these options were not given to you? Let's say that these options were in fact not given to you, and we were required to find the line. So first of all, we know that any line that is supposed to be perpendicular to this line should have a slope of -1/2. Okay, so the equation should look like -1/2x. Now what we are left with is the intercept. Okay, we can try to find out the intercepts, but that's going to take us a long time, because we could have infinite amount of options. So instead, what we do is make use of the point slope form of the line. What is the point slope form of the line? That is y minus y1 is equal to m into x minus x1. If you're given a slope, and if you're given the coordinates of a point, you can use this form and identify the equation of a line. So we have just identified that the slope of the line should be this. But if that line is also supposed to pass through points 3 and 1, we are given this point. So this 1 is your y1, and this 3 is your x1. So instead, let's substitute these, these coordinates in this line. We have already given m is equal to -1/2 as the slope. And let's just substitute these coordinates, x instead of x1 and y1, and let's see. So y minus 1 is equal to x minus 3, because the slope is being multiplied by the difference of x minus x1. Okay, and if you solve this, you're going to get this line, which was our answer. Okay, but again, why we didn't take this way, we didn't use this way, is because we eliminated these two options first, and we substituted this point in this line, and we found out that this was also invalid. That leaves us with this option, and that is correct. Okay, great. Okay, moving forward, and this is, for example, so this is the equation of the line. So let's see, we can see that 3, 1 is not the intersection, but 3, 1 indeed lies on the line that we found out. So y is equal to minus, this equation of a line, y is equal to -1/2x plus 5/2. So this is this line, and 3, 1 indeed lies on this line. Right, great. All right, okay, wonderful. Moving forward, okay, I'm trying to, again, I'm this for this problem, I'm going to let you solve it, okay, at your own time. So I want you to write this down, okay, because and I'm just going to give you the method for this. So from the given options, choose the point of intersection for the lines y is equal to x minus 4 and y is equal to -1/2x minus 5, and the options are not given to you. Okay, so how do we solve this? We have actually covered this earlier, but I'm going to do that quickly. So one line is y is equal to 2x plus 4, and the other line is y is equal to -1/2x minus 5. Okay, first of all, because here we can see that we can see that these two lines are perpendicular to each other. So they should definitely intersect, because I mean, if the slope was different, they would intersect. But over here, we can also identify that these two lines are perpendicular, because the slope of one line is actually the negative reciprocal of the other line. So definitely intersecting. And now, let's say they intersect at point x1 and y1. Okay. And then what we do is we plug in, or we substitute x1 and y1 in both of these equations. So y1 is equal to 2x1 plus 4, and y1 is equal to -2x1 minus 5. And why is this? Because let's say if we have this line, any two lines, not necessarily these two lines, any two lines, if they are intersecting, both of them should pass through the same point. So over here, x1 and y1 represents the point where these two lines intersect. So in fact, this point should satisfy both of these two conditions. Okay, so what we can do now is equate. All right, so this is equal to y1, this is equal to y1. Y1 is already isolated at one side, so we can equate these and these two. So 2x1 plus 4 is equal to minus 2x1 minus 5, okay? And if we solve for x1, we are going to get something. Let's say x1 is equal to a, all right? And in this particular case, this a is minus 3.6, all right? And if we substitute this value in either of these equations, either this equation or that equation, if we substitute the value of x in either y is equal to 2x minus 4, or we substitute the value of x1 minus 3.6 in this, we're going to get the value of y, which in this particular case is going to come out as b, which is minus 3.2. Okay, so you can solve this, and let me show you why I know these answers. Is because I use the graphing method, and I've also solved this, but this is for illustration purposes. That said that both of these, intersect somewhere over here in the negative quadrant. So minus 3.2 and minus 3.6. Yeah, exactly. Right, great. Okay. And that brings us to one of the most challenging topics on, in coordinate geometry, that is faced by a lot of different students. A lot of different people kind of face challenges when we're discussing the concept of regions. Okay, so I hope that the examples are clear, and I want to move forward. Again, why the concept of regions, I'm trying to discuss this, after the examples, is because now through those examples, we understand how to, utilize all the knowledge of coordinate geometry, the equation of the line, the slope intercept forms and everything, and how to solve different questions. And we're going to make use of that same knowledge, and we're going to, for example, identify the regions. Okay, so what is a region? A region is an area that satisfies a certain condition. Okay, if for those of you who started with us, what we started off earlier was the first line, which was x is equal to 2. Okay, and what was x is equal to? We remember that if this is a special case of a line. Why? Because if you're given x is equal to 2, this line is parallel to the y-axis at which point? X is equal to 2. So this is our x-axis, and this is our y-axis. Okay, line. Yeah, great. So this is a line that is parallel to the x-axis. Okay. So what would be a region that is, defined by this? So this is the equation of a line. This is the expression of a line. Let me change this. Let me change this to x greater than 2. So now, all the values of x that are greater than 2 should satisfy this expression. Okay, so x is greater, over here. Any point to the right, it's x is greater than x. This x is equal to over here. So this is 2.1. Maybe this is 10. Extend this further. Maybe this is 1,000. Going by a logarithmic scale. Just numbers. Okay, but the point is that once we start moving right of x is equal to 2, all those are going to be greater than x. But here's the the point. That is also, this point is also x is equal to 2.1. If this was in line with this, let me just draw this more clearly so that you can understand what I'm trying to tell you over here. So this is your line, x is equal to 2. Okay, and this is, let's say, 2.5. Okay, so this is greater than x is equal to 2. This point satisfies this expression x greater than 2. But so does this point, and this point, and this point, and all of these points that lie to the right of this line satisfy, for example, this condition that for all of these lines, for all of these points, the value of x is greater than 2. So now this actually does not represent a point or a line, but this represents this entire region that lies to the right of this line. All the region, all this area that lies to the right of this line is, correct. This satisfies this expression x is greater than 2. Okay, I hope that this has made sense to you, and I'm going to quickly do that once again. Okay, let's say we have the same line, x is equal to 2, right? X is equal to 2. This is your x is equal to 2 line, and now we change the condition. Instead of saying x is greater than 2, we say x is less than 2. And now what is going to happen is, along the x-axis, any point that has a value of x that is less than 2 is valid. But then it is not only the points on the x-axis, but every point along the x-axis which has a value of x coordinate less than 2. So let's say this point, x is equal to 0, perfectly valid. But all of these points along the y-axis also have the x coordinate less than is equal to 0, which is less than 2. So any point over here, x is equal to 1, valid. But any point over here has x coordinate less than 1, so valid. All the points over here, valid. All the points over here, valid. So points over here, valid. So now what we identify is that there could be infinite number of points, that constitute this or these lines. Okay, so instead of talking in terms of points or lines, we talk about regions, so that the region that satisfies this expression is a set of all points, that lie to the left of this line, x is equal to 2. So this is the region that corresponds to x less than 2. I hope this is clear. Why we are talking about regions is that because now this is an entire collection of points. We can no longer fit one line, or we can no longer, call it one point. In fact, this is a collection of all these points. And when it becomes a collection of all these points, this becomes the entire region. Okay. And here's a fun fact. Okay. If I said that, what will, I'm just going to quickly ask you for that. If I say, find out the region for x as a real number. Okay. So far we haven't considered the real numbers, but real number is any number, negative, positive, any number, decimal, rational, irrational, all numbers. So if x was a real number, okay, so for this, the entire xy plane would actually be satisfying this condition. Okay, so this is just a fun fact, not really very related to what we were discussing right now. Just wanted to share this with you. Okay, so going to another example. Okay, we have your xy plane, and let's say we've got y is greater than -4. So first of all, to identify, I'm sorry about that, y is equal to -4. So first of all, what we need to do is identify the boundary of the region. Okay, and how do we find out the boundary of the region? We convert this inequality sign. So there is either an equality sign or any other sign, whether it is a greater than, less than, or not equal to, that is an inequality. That represents an inequality. Okay, so we change this inequality sign to the equality sign. So let's say this is y is equal to -4. Okay, and let's first draw this line. Where is y is equal to -4 going to be? it's going to be below the origin and it's going to be parallel to the x-axis. Okay, so it's going to go something like this, right? So this is your y is equal to -4 line. And now, so this line we have drawn, and why? What is the significance of this line? This line represents the boundary of the region. Okay, this line represents the boundary of the region. And now, because the expression that we are supposed to find out is y is greater than -4. Y is greater than -4. Yes, great. Y is equal to y is greater than -4. So any point that has a y coordinate greater than -4 is a valid point. So any point over here. Why? Because this may be -3. So over here, the x coordinate could be anything, x1 and -3. Okay, but because -3 is greater than -4, this is valid. Okay, so this point is valid. Something over here is valid as well. Any point over here is valid as well. So all of these points are valid. Okay, so let's now draw the region. What the region is going to look like is all the set of points that lie above this line. Okay, yes, I'm going to come to whether the boundary is included or not so far, because this is strictly greater than. Okay, so the equation says that y has to be greater than -4. So this is the boundary, not part of the region. And any point that lies above this line, that lies above this line is a valid region. Okay. And so this is, I hope that this concept of regions is clear. And now, to talk about a different inequality. Say you have y is less than or equal to 1. All right, again, first of all, we change this to the equality sign so that we can identify the boundary. Okay, we can identify the boundary. Okay, so this will become y is equal to 1. All right, so where is y is equal to 1 going to lie on? Y is equal to 1 is going to be somewhere over here. Right, so this is your y is equal to 1 line. And then all of these points are going to be less than. So this part, all of these points over here under this line are going to be less than y is equal to 1. But the interesting thing is that we're supposed to identify all the coordinates, the y coordinates, which are less than or equal to 1. So equal to 1, all the points that lie on this line, have a y coordinate equal to 1. So this is a special case. Why is it a special case? Because the region includes all the points, or is a collection of points that lie on or below this line. Yes. So in this special case, the boundary is also going to be included. So if I said, so for example, let's say, here's a quick example for you. Okay. So I'm going to give you a point. I'm going to say y greater than equal to 2 and identify whether a coordinate lies in this region or not. I'm going to say 2 minus 2. This is one option. Okay. And 3, 2. So, okay. And then the last option is 5 and 1. Okay. Which of these three options satisfy y greater than 2? Y greater than or equal to 2? It is going to be this option only. Why? Because this has a y coordinate of -2, strictly less than. Okay. This has a y coordinate of 1, again less than 2. Okay. And this has a y coordinate of 2. Okay. It is equal to 2, and our condition says that any y coordinate which is either greater to 2 or equal to 2 is valid. So this point is, a valid part of the region that is defined by this expression. Okay, so this was, just a quick example of how we can ascertain without actually having to draw the region itself. Okay, I hope that this concept is clear. We're going to, quickly look at some of, other examples as well, so that we can actually look at more complex cases of how regions are defined. Okay, right, moving forward. Okay. Interesting. Now we're supposed to plot x plus y greater than 3. Previously, what we were doing was we were having lines that were either parallel to the x-axis or the parallel to the y-axis. It's a different line, but the procedure remains the same. First of all, what we do is we change this inequality to an equality sign. X plus y is equal to 3. Okay, but this is not something that we've seen earlier. This is, in fact, the same thing that we've been seeing before as an equation of line. Why? Because if we just change this thing slightly, we take x to the other side. So what does this look like? This is the standard equation of a life in the equation of line, the slope-intercept form. The slope is m is equal to -1, and the y-intercept is 3, okay? So let's, quickly draw this line. The line is y is equal to minus x plus 3, okay? Here is our xy plane, okay? So the slope is negative. The slope is negative, and so it's going to look like something like this. So its x-intercept is going to be 3. Sorry, the y-intercept is going to be 3 because you simply plug in 0 over here. So we get y is equal to 3. And the x-intercept is also going to be 3. Again, because the slope is unity, negative unity, but unity, the magnitude of the slope is unity. So the x-intercept is also going to be 3. And now, how do we identify this region? So we have found out that this is the boundary. This indeed is the boundary. Okay, right. And so how do we figure out the region where x plus y indeed is greater than 3? Okay, let's look at this point over here. Let's look at this point. This has, x is equal to, 1. And the corresponding, y is going, what is the corresponding y going to be? We can quickly do that by simply, substituting the value of x over here, okay? If the value of y is 1, okay, so the value of y is going to be, sorry, this should simply be -1. Quickly, let me do that. So I've just substituted the value of x over here. So the value of y is going to be 2, okay? And x plus y, so this is 1 plus 2 is equal to 3. But what we want is strictly greater than 3, right? So this line, so over here, let's take a look at this point. Okay, at this point, your x-intercept is 0, and so the value of x plus y is going to be 3. Over here, if we look at this point, the value of y is again going to be 3. Sorry, the value of x plus y is going to be 3. Over here, the value of x plus y is going to be 3. Over here, the value of x plus y is also going to be 3, is equal to 3, okay? Okay, so 2 and 2. All right, let's draw this value, this point 2 and 2. Okay, so where is this point 2 and 2? Let's quickly take a look at this point. Right. So let's take a look at this point over here. Right. So this is our line. X plus y is -3. So you have your y-intercept. You have your x-intercept. Okay. So okay. Right. So 2 and 2, okay? So this is a valid point, okay? So this point is valid. Why is it valid? Because if we plug in x, so this is y is equal to -x plus 3, okay? Right, so 2 and 2 point is definitely part of the region, but it's not going to lie on the line. Why? Let me quickly show you. Why? It's because you have y is equal to -x plus 3. If we substitute 2 over here, what are we going to get? We're going to get y is equal to -2 plus 3. So you're going to get, -2 plus 3 is 1. So the corresponding point on the line is going to be 1. So if you have y is equal to, sorry, x is equal to 2, the corresponding point on the line is going to be 1. And point, the coordinates that are given 2 and 2, they are going to lie above the line. Okay, they are going to be above this line. No, the point what I'm trying to explain right now is that this point marks the boundary. Okay, and what I was just trying to do is trying to show you that all the points that are below this line, always, the maximum value is going to come out as 3. So for all the points that lie in this side, for them, the maximum value is going to be 3, or it's going to be less than 3. So the valid region in this particular case is going to be everything that is to the right side of this line. Okay, every point that lies to the right of this line, to the right side of this line, is going to satisfy this equation. And because we have a strict greater than sign over here, this boundary is not a part of this value. Why not the upper? Right. Okay. Here's the thing. Over here, let's say, so this value. So what is this value going to be? Let's say you have 3 over here. And if you go to, let's say, 4, let's say y is equal to 4, what is the corresponding x value going to be? The corresponding value of x is going to be, you can simply, substitute that value. Y is equal to minus x plus 3. Okay, if we plug in y is equal to 4, okay, and so this is going to come look like y is equal to 4 is equal to minus x plus 3. Okay, you bring in minus 3 to the other side, so this is 4 minus 3 is equal to minus x, and so this implies that 1 is equal to minus x, or x is equal to minus 1. So x is going to be minus 1, and if we add 4 plus minus 1, the result is going to be 3. So the maximum value that you can get on the left side of this line is going to be 3. It's never going to exceed 3. Why? Because this line satisfies this equation, x plus y is equal to 3. This line has, all the values for which x plus y is 3. And any point that is to the left of this line is going to be x plus y is less than 3. And any point that is to the right of this point is going to be x plus y is greater than 3. Okay, let's quickly, for example, recap this, why this is important. Okay, it's important is because the lines represent the boundaries. So if you're given, an inequality, first of all, convert the inequality sign to equality, and plotting that is going to give you your boundary. Okay, and then you can find out 2 and 1 satisfy? No. Why do 2 and 1 not satisfy? Is because, for example, okay, yeah, sure, we can do that. 2 and 1 don't satisfy is because when we do 2 plus 1, we get 3. But what we wanted was x plus y is strictly greater than 3. Okay, there's a strict greater than over here. All right, so if this was x plus y is greater than or equal to, then the point 2 and 1 would satisfy. But otherwise, they're always less than. Okay, let's quickly do that. Let's quickly do that. Let's say we have this line. Let's take a simpler line so that we have a better grasp on things. Y is equal to x, or x is equal to y. Written both ways, this is the same. So you have this line with a positive slope. Y is equal to x. Okay. So y is equal to x is going to look like, sorry, this is slightly shifted, but we're not taking a shifted line. This is your y is equal to x line, right? Let's say what we wanted was x greater than y, all right? So first of all, what we do is we change this inequality sign to equality. So we write y is equal to x, or x is equal to y. And this is this line over here. And now, so this represents our boundary. And what the question is asking us is to identify the region which has x greater than y. All right. Okay. So let's take a look. So all the points on this line have x is equal to y. So this should have actually gone, slightly more horizontal, so that, we actually something like this, if we draw it more accurately, something like this. So on this point, on this line, you have x1, y1. On this point, you have x2, y2. This point, x3, y3. Okay. So this is our boundary. So this is the boundary where x is equal to y is satisfied. Okay. Right. Now, how do we find out? So for example, let's take this value over here. This any point over here. Let's take this point over here. Okay. For this point, the value of x is 1, but the value of y is around, let's say, 0.6, right? Somewhere over here. Or this is 0.4, in fact, 0.4, 0.6, 0.8, and 1. Okay, so this is a valid option. Why? Because the x is greater than 4. If we take a look at this point right over here, okay, x is going to be 2 and y is going to be 1.8. All right. So again, this is also a valid point. So this tells us that all the points that are lying under this line, all right, the region that is below this line satisfies our mandated requirement, which is x greater than y. We can, in fact, extend it to the third quadrant as well. So for example, let's take a look at this point over here. All right, this point over here. Okay, let's take a look at this point over here, this red point below this line. Over here, x is -1, but y is -1.2. All right, because this point is -1 and -1 over here. Let me quickly, change the color. This point is -1 and -1. So if I go below this, what I'm actually doing is I'm moving to more towards the negative x-axis. So if, for example, if I were to move somewhere over here, the x coordinate is going to remain -1, but the y coordinate is going to be over here -2.6. And for this point as well, the x is greater than y. So all the points below this line satisfy this expression x greater than y. Okay. I hope this is clear. This is, clear to you guys. Okay. So, and we're going to do one final, example with the positive slope. And let's say we have, x plus y is going to have a negative slope. Okay, so let's just quickly write down the same equation. Y is equal to x plus 1. Okay, we have this line, y is equal to x plus 1, which means that this is going to look something like, not exactly like this, but it is going to pass through -1 and 1, and this is your line. This is this line, y is equal to x plus 1. The y-intercept is 1. The x-intercept is, we plug in 0, take 1 to the other side, this becomes -1. So you get, both the x and the y-intercepts are drawn correctly. Okay, and what we want is, an expression which has, for example, let's say, y minus x is greater than 1. Right? How do I did that? For example, I just took x to the other side. So this is y minus x is equal to 1. And I did that in a roundabout fashion. So initially, what was given to us was this expression, y minus x is greater than 1. And so what I did was I changed this inequality to the equality sign. So this becomes y minus x is equal to 1. And when I took x to the other side, that became x plus 1. So this is this line, x plus 1. So in fact, the question would have stated, find out the region, for example, for which y minus x is greater than 1. All right, so y minus x is greater than 1. So first of all, we identified that this is the boundary. This is your boundary. Okay, so this is y is equal to x plus 1 boundary. Or or for example, yeah, so this is your y minus x is equal to 1 boundary. Okay, and so what we want to find out is that which points are going to be greater than 1, right? So first of all, over here, let's take a look at this point over here, or maybe this point over here. This is a point that has -1 and -1. All right, and if we do -1 minus -1, all right, y minus x. So this is your y, and this is your x. So -1 minus -1. So this is -1 plus 1. This is 0. All right. So this point is 0, does not validate or does not, belong to the correct region, because we want to find out where y is greater than x by at least a single digit. Over here, we see that this line, let's take a look at a simpler option. Okay, this line has y coordinates as 0 and 1. And the corresponding coordinates are, so for example, 1 minus 0, y minus x is equal to 1. So this is your boundary line. But if we go over here, if we go to this point, and if we say, okay, what are the coordinates for this point? This is 0 and 2. Now, what we want is the region where this, for example, condition is satisfied. So 2, which is your y coordinate, minus 0, which is your x coordinate, gives you 2. And this, in fact, is a valid point. All right. So this gives us an idea that any point that lies above this line is going to belong to the valid region. Okay. So let me quickly redraw this for, clarity's sake, before, calling it off. Okay. So the original expression was, or, the original line over here was y is equal to x minus x, y is equal to x plus 1, right? So something like this. All right. And what we were supposed to find out was the region that satisfies y minus x is greater than 1. So we understand that this is the boundary. So this is y minus x is equal to 1, because all of the points along this line, on this line, satisfy. So this is an example. This is an example. This is my example. All right. So this is my example. I want to, plot the region where y minus x is greater than 1. Okay. The question states, okay, the question states that find out the region where my y minus x is greater than 1. So first of all, what I did was I changed this inequality to the equality sign, and I got y is equal to y minus x is equal to 1. I changed it into the slope intercept form, and I drew this line, and this is this boundary. This is, any coordinate on this line satisfies y minus x is equal to 1. You can check this. So for example, over here, so this is your x-intercept. What is your x-intercept? X-intercept is -1 and 0. And so what is the, for example, the governing equation? The governing equation is y minus x. So let's subtract x from y. 0 minus -1. So 0 plus 1 is equal to 1. So this is your boundary. So this satisfies y plus x is equal to 1. So this is your boundary. And now what we want to find out is the region where y plus x is, or sorry, y minus x is greater than 1. We want to find out y minus x is greater than 1. So this region, okay? Let's take this point over here. This point has the coordinates 0 and 2. So 2 minus 0 is, as per y minus x, we do 2 minus 0, and so this is, the value is 2. So this is valid, okay? Let's take this point over here, okay? This point has the, the coordinates of 1 and 0. Okay, and if we do the same thing, y minus x, so in this case, this is going to be 0 minus 1. So this is going to be -1, which is incorrect, because we want y minus x, the answer of y minus x should be greater than 1. Whereas for this point, the answer for y minus x is -1, which is why this point is incorrect. Okay, we can continue with this, but these 2 points, let's take this point. Let's take this point over here. What are the coordinates for this point? The coordinates for this point are -2 and -2. All right. And so if we do y minus x, so this is going to be -2 minus, what is the value of x? Is -2 over here. All right. So this is y -2. Sorry, this is not -2. This is actually +2 because this point is over here. This point is +2 over here. Okay. So the value of, let me quickly redraw. All right. Let's take this point. The coordinates for this point are -2 and 2. Okay. Yeah. Thank you very much for pointing that out. Thank you. Right. So y minus x, 2 minus, this is the value of y, minus, what is the value of x? -2. This is the value of x. So 2 minus -2 becomes 2 plus 2, which is 4, and greater than 1. So this point is valid. Okay, so we have taken 2 points. We have taken 2 points, and this tells us that all of this region that lies above this line holds, or holds, or is a collection of all the points that satisfy y minus x is greater than 1. Y minus x is greater than 1. All right, let's, just for clarity's sake, let's do one more example before calling this session, right? And that is, say, y minus x is less than 2, right? I've changed the example so that, we don't build on the lessons of the previous one right away. And so let's look at this. First of all, we have to change this inequality sign to the equality sign. Step 1, y minus x is equal to 2. Convert it into the line, the slope intercept form. Step 2, y is equal to x plus 2. Okay, right. Now let's plot this. So the intercept of x is going to, the y-intercept is going to be 2, and the x-intercept is going to be -2. All right. So this point and that point over here, right? So this is your line, y is equal to x plus 2, or this is, this line satisfies, or all the points on this line satisfy this expression, y is equal to x minus 2. So this is your boundary. And what we are supposed to find out is that the difference between y and x should be less than 2. Okay? The difference between y and x should be less than 2. Okay, let's take this point over here. Where am I? Okay, let's take this point over here. This point, right? So the coordinates are 0 and 3, right? And so what we do is, when we do 3 minus 0, the answer is 3, which is greater than 2 over here. So this point is incorrect. This point is not correct, right? Let's take another point somewhere over here, this time over here. So the coordinates of this point are -3 and 1, okay? And now if we do y minus x, so this is y, what is the value of y? Y is 1. What is the value of x? X is -3. And so once we've solved it, so this is, sorry, y 1 plus 3 is 4, which is again greater than 2. Okay, so this point is also invalid. So we see that we try to find out the plots over here above this line, but they are all coming out as incorrect. We have taken 2 points and they are incorrect. Okay, so this gives us safe assumption. Now we move to a point that is, let's say, below this line, right? Let's take this point over here, right? -2 and -2. Okay, so what does y minus x mean? Y minus x for this point means -2, right? Which is this -2 over here, minus and this is your x coordinate. So this becomes 2 minus 2 plus 2, which is 0. And this is definitely less than 2 over here. So this is a valid point. This point is valid. This is correct. So this tells us that, the points under this line, the points that are, say, under this line are all the points for which y minus x is going to be less than 2. And all the points that are above this line will have, y minus x greater than 2. And because, yeah, so far, yes, we want to be confirmed about the regions, okay? So the simplest way is to go either 1 point above or 1 point below, because this is the boundary. This is the boundary. So for this boundary, y minus x is equal to 2. So it is going to be above or below this, okay? So because we were supposed to find out this expression, y minus x is not equal to 2. In fact, it is less than 2. So either this region or this region is going to be a valid option. So what we do is we take any arbitrary point and we plug in the value, and we say that whether this expression, whether this relationship holds. So we have seen that over here, all the points over here that we've tried to find out, those, for example, do not hold. We've taken 2 points, and for both of them, their values are greater than 2. All right. So let's take you finally for one final option. Let's take this value. This is the coordinates for this point are -4 and -1. I'm going to write this over here, -4 and -1. And let's do y minus x and see whether it is indeed less than 2 or greater than 2. So -1 minus, so this is your y, and this is -4. So this is going to be -1 plus 4 is equal to 3. And this is greater than 2. So this point over here, which we just picked, this point over here, this indeed lies above the line and therefore does not satisfy our governing expression. So we have seen that we have taken 3 points, and all of the points that are above this line do not satisfy this equation. So we can safely state that all the collection of points that lie below this boundary, satisfy this expression y is equal to x minus y minus x is less than 2. So a collection of all the points or the entire region below this line satisfy this expression y minus x is less than 2. Okay, so I hope this is clear. I wanted to wrap this today, but there are some aspects remaining, and we're going to cover them in the next session, not the regular session that we hold, but this special session. So in that, we're going to look at the absolute values. We're going to look at the absolute values and how absolute values are supposed to be plotted on the XY plane, especially when it comes to the regions, okay? So with this, we come to the end of our session today. Thank you very much for